A classical electron is moving in a circular orbit of radius 1 angstroms with angular momentum h bar. This is the previous problem. Now we're going to calculate the magnetic dipole moment of the electron, giving the answer in SI and CGS units. SI and CGS. And then calculate the magnetic dipolar energy of the circulating electron when it is in the field generated by a second identical circulating electron at a distance of 3 angstroms away along its axis. Assume that the magnetic moment of the first electron is aligned parallel to the field from the second electron. So if I have an electron that is circulating like this, you can see that the current is basically opposing the direction of motion of the electron, and we can find the magnetic moment, magnetic dipole moment of this electron by looking at the dot product, by looking at the current times area. So magnetic moment is basically as a vector quantity, it is current times the area vector, and the area vector is pointing down here. So this is the area vector that is basically found by using the right hand rule. If you curl your fingers in the direction of the current, the thumb points in the direction of the area. So magnetic dipole moment is current times area. So if this is the z-axis, then it will be in the minus z hat direction. So we can calculate the magnetic dipole moment of the electron as minus, because we have calculated already the current that is due to this circulating electron in part A. The current that we found was minus 3 10 to minus 4 amps. So it is minus 3 10 to minus 4 amps, and the area is pi r squared, so pi 1 10 to minus 10 squared. So this is basically minus I, and it's in minus z hat direction, so minus I pi capital R squared z hat. So if you calculate this, you will find that the magnetic dipole moment of the electron is minus 9.4 times 10 to minus 24 ampere meter squared. So this is one way to write it, or you can write this as joules per Tesla. It has 2 SI units. And now we need to calculate it also in the CGS units system. Since 1 joule is 10 to 7 ergs, 1 Tesla is 1 Weber per meter square. That is equal to 10 to 4 Gauss in CGS units. We can write this as the magnetic dipole moment is equal to minus 9.4 times 10 to minus 24 times 10 to 7 ergs divided by 10 to 4 Gauss, so joules per Tesla. Therefore, we find that in CGS, this is in minus z hat direction, magnetic dipole moment is minus 9.4 10 to minus 21 ergs per Gauss, and this has a name in the CGS system. The magnetic dipole moment of the electron is minus 9.4 10 to minus 21 electromagnetic units in the CGS system. So the magnetic dipole moment in the CGS system is minus 9.4 10 to minus 21, and in the SI system is minus 9.4 10 to minus 24 amps meter square, or joules per Tesla. Now, how do we obtain the joules per Tesla? That will be clear in part C. Now, I want to note that there is an interesting result here. The magnetic dipole moment given in terms of a Bohr magneton. So, a Bohr magneton is equal to EH bar divided by twice the mass of the electron. So it is 1.6 10 to minus 19 coulombs, 6.63 10 to minus 34 joule seconds divided by 2 pi, so it would be 4 pi, 9.11 10 to minus 31 kilograms, and this actually gives us 9.4 10 to minus 24 joules per Tesla. So therefore, the answer that we have found is, so the magnetic moment of the electron is minus a Bohr magneton in the z hat direction. So I can also write it in terms of the Bohr magneton. So an electron circulating with a classical electron circulating with a radius 1 angstrom has a magnetic dipole moment exactly equal to a Bohr magneton when it has angular momentum h bar. Now let's calculate the magnetic dipolar energy of the circulating electron when it is in the field generated by a second identical circulating electron at a distance 3 angstroms from its axis. So this is part C. The magnetic dipole energy in SI units is given as minus mu 0 dot product of magnetic dipole moment with the magnetic field. So this is in SI. It is minus m dot h in CGS. Now you can see that the energy is given in joules, and mu 0 times h has the unit Tesla in SI. So we have joules equals to the unit of the magnetic dipole moment times Tesla here. So the unit of magnetic dipole moment in SI is joules per Tesla. So that's the unit. So therefore, what I have done in part B was correct. It's ampere meter square or joules per Tesla is the unit, the SI unit, let's say, of the magnetic dipole moment. So here I have used mu electron, so you can use mu or m. So let's be consistent here. Let's call this m. That's what we have calculated. Now here we're going to calculate the magnetic dipolar energy. So U will be equal to mu 0, which is 4 pi 10 to minus 7 Henry per meter times magnetic dipole moment of the electron. So here I have to be careful with the direction of m and h. Now it says that assume that the magnetic moment of the first electron is aligned parallel to the field from the second electron. So the dot product will give me basically m times h. So this will be 9.4 10 to minus 24 multiplied with the magnetic field that I have calculated in part A, 47,434, or I can write this as 4.74 if I round it, times 10 to 4 amps per meter. So I find the magnetic dipole energy as minus 5.6 times 10 to minus 25 joules. So this is magnetic dipolar energy. And if I convert this to CGS units, this is going to be equal to, since 1 joules is 10 to 7 ergs, we can write this as magnetic dipolar energy is minus 5.6 times 10 to minus 25 times 10 to 7, which will give me a minus 5.6 times 10 to minus 18 ergs as the magnetic dipolar energy in CGS units. So this is CGS. So here basically I have substituted for m dot h equals m times h, since we are assuming m vector is parallel to the magnetic field created by the second electron. So this is basically mentioned here. The magnetic moment of the first electron is aligned parallel to the field from the second electron. With that assumption, I get a magnetic dipolar energy minus mu 0 m dot h. M dot h becomes m times h. Okay, so for the electron that we discussed in the previous problem, that is moving in a circle with constant angular momentum h bar joule seconds and radius 1 angstroms, we calculate the magnetic dipole moment of the electron in SI and in CGS. Magnetic dipole moment in SI is given as current times the area. The magnetic dipole moment in CGS is pole strength times the distance between the poles. So this is the CGS, and as a vector, so if you look at plus p and minus p here, these are at a distance L from each other. The magnetic dipole moment vector points from minus p to plus p. So this is the magnetic dipole moment vector m, and it has a magnitude p times L, the distance between the two poles, identical poles with opposite signs. So this is in the CGS definition. Okay, so using the SI, magnetic dipole moment is current times the area vector, where area vector is defined using the right hand rule. If you curl your fingers in the direction of current, the thumb points in the direction of the area vector, and area vector has a magnitude area, which is pi r squared. So we multiply the current with the area vector, we obtain minus 9.4 10 to minus 24 amps meter square, or joules per Tesla in SI units. And the joules per Tesla comes from the magnetic dipole energy. U is equal to minus mu 0 m dot h. Mu 0 times h has the unit Tesla. Why is that? Because we have the relationship between B, H and M. Mu 0 times H plus M in SI units. This is the constitutive relationship. So mu 0 H and mu 0 M both have the unit Tesla. Therefore, we have joules per Tesla as the SI unit of magnetic dipole moment. So 1 joule is 10 to 7 ergs, 1 Tesla is 10 to 4 Gauss, converting to CGS units here. If I substitute these, I find that it's minus 9.4 10 to minus 21 EMU. EMU is the unit of magnetic dipole moment in CGS, which is ergs per Gauss. And I noticed that it is exactly equal to a Bohr magneton. For the magnetic dipole energy, I first checked the angle between M and H. It's mentioned in the problem statement that they are parallel. So the energy is minus mu 0 mH. M was calculated in part B. H is calculated in part A, 4.74 10 to 4 amps per meter. So that is here. So substituting these values, and mu 0 is equal to 4 pi 10 to minus 7 Henry per meter, permeability of free space. This is Henry per meter, that H is Henry. Okay, so we obtain minus 5.6 10 to minus 25 joules, and to convert the CGS we just multiply with 10 to 7, since 1 joule is 10 to 7 ergs. We obtain minus 5.6 10 to minus 18 ergs.